Okay. Hello, welcome back. For the past 4 weeks we have been talking about static systems. We have been talking about how static systems can be analyzed. We have looked at trusses, we have looked at beams, we have looked at friction in a very elementary way. We are going to switch gears and start talking about movement, motion starting today. The first step in understanding motion is to study motion in the context of how it actually happens. Then comes the idea of a force that causes the motion. So, we will progress in that same logical fashion. We will start by analyzing motion, and the study of motion is what we refer to as kinematics. So, we will begin our discussion of kinematics with particle kinematics, and for the sake of completeness, kinematics is the study of motion without paying attention to the forces causing it. So, what would be an example of something like this? Let us say I have a particle P moving along some trajectory on a plane xy. The first point we have to understand is the observer. Who is the observer? So, the observer in general can be fixed or moving, and when that person or observer is moving, that person can be moving with a constant velocity or even accelerating. We will look at all of these 4 scenarios in detail a little later, but first let us understand how to analyze a particle moving on a trajectory such as this. For example, that could be a car that is driving along a road such as this. There are 2 ways we can analyze this motion. Having fixed the observer, the observer is, let us say in this case, fixed. We are going to make things simple. Now, I can choose an independent coordinate. So, this is the next choice that one would have to make. The first choice is who is the observer and what is the observer's state, whether the observer is fixed or moving with a constant velocity. The second is what is our independent coordinate. The independent coordinate also has 2 choices. I can make observations with time as my independent coordinate. So, for example, the particle is at some position at t equal to 0, it could have moved to another position at t equal to 1 second, a third position at t equal to 2 seconds, and so on. Let us say the particle slowed down around a bend, so it did not move very far in that 1 second, as you can see in the sketch here. So, I know the position of the particle at each of these instants of time. Another possibility of making observations is with spatial coordinate as my independent variable. So, it could be x, it could be y, it could be x and y, depends on the number of variables I need to completely describe the motion of this body. Okay, we will come to this later. Let us first talk of what the time analysis looks like. So, when I begin to make observations being at the fixed frame of reference O and using time as my independent coordinates, what I end up recording is at various instants of time t1, t2, t3 dot dot dot. I know the position x1, x2, x3 and the y position y1, y2, y3. So, I know that at various instants of time I know the x position, I know the y position. In addition, so this is the first level of observations. In addition, I can look at the vector along which the object was moving, the car in this particular instance. And let us say if the car has a speedometer in it that is indicating a speed, I can also record from the speed, from knowing the speed and from knowing the instantaneous tangent vector, I can essentially record the u velocity and the v velocity. U and v are components of the velocity in x and y directions. So, I could record a u1, v1, u2, v2, u3, v3, etc. So, notice how in this particular way of making our observations, x and y are dependent variables. And time is the independent variable. So, if I now come back and look at making sense of this, what do I want to understand? I want to understand, let us say the position of this point. So, I can now do things like plot the x position versus time, y position versus time. I can also from these observations plot, let us say, the velocity versus time. But one would have to understand that the velocity itself is not unrelated to the position, and that is our basic laws of kinematics, at least that says that in one dimension, we will write these down for one dimension and then generalize, u equals dx dt. So, if I know if x position is known at an instant t and a second instant t plus delta t, then the x velocity given by u is defined as the change in position in the time interval delta t divided by delta t. And a contribution coming from calculus is that if I let this delta t become very small, then I end up recovering the actual velocity at that instant of time, x component of the velocity at that instant of time. So, one of the biggest contributions of calculus was this idea of instantaneous velocity. So, if I now can record the positions of this particle not just at discrete instants of time like shown here 1 second apart, but if I am able to make observations such that this delta t, which is 1 second in this experiment we did very early on, if I let this delta t time span become smaller and smaller, the ratio of the change in the position to the actual time space between the two observations gives me a better and better estimate of the instantaneous velocity in the x direction, which we indicate by the letter u. So, think of it this way, a way to say this statement in English is as I make delta t smaller, I get a better estimate of u at the instant t, at the time instant t. So, if I am interested in the actual velocity of a body at a particular time instant t, I can start with 1 second like we drew in the picture earlier, but if I have the ability to let that time span 1 second become smaller and smaller and smaller, I recover a series of numbers which will converge to one number u, and that number is the instantaneous velocity of this vehicle at the time instant t. Now, if you will notice, if I can never actually get to delta t being 0, because that would give me an indeterminate ratio. So, we have to create a sequence of numbers where delta t is becoming smaller and smaller and smaller, and that sequence converges to a number called u. This is basic calculus being used to understand motion. Of course, there are some riders to it which comes in basic mathematics associated with calculus, that this function x as a function of time is continuous and differentiable at the instant t. Okay. So, given that this ratio x at t plus delta t minus x of t, the change in position divided by delta t, converges to one number u. So, having understood the idea of an instantaneous velocity, can I now take this one step further and understand acceleration? We all know the basic definition of acceleration, which is given by rate of change of velocity. And our old mathematical calculus definition is that A in one dimension, A equal to du dt. Again, if we use the same calculus definition of A equal to u at t plus delta t minus u at t divided by delta t, limit delta t tending to 0. So, if I have this particle, I am going to redraw the sketch here just for the sake of ease of following. If I know that the particle is at some position t and I know its velocity u at t, if I record its velocity at a second instant t plus delta t. Now, in this time span, the particle executed this kind of motion on that bold piece of road. If I subtracted the velocity at t plus delta t minus the velocity at t. Now, I am doing this in one dimension, but the sketch shown is not in one dimension. So, we have to be clear that if I had a one dimensional road and I know the velocity now and the velocity at a short time later, if this is the distance travelled and the time separation is delta t. Now, as I let this delta t become smaller and smaller, this ratio u of t plus delta t minus u of t, the change of velocity divided by the time spacing between the two measurements, between the two observations, again converges to a number a as this time spacing becomes smaller and smaller. So, I can do the same experiment where I record the velocity 1 second apart and now let this time spacing become smaller and smaller, and it gives me a series of numbers. The first number, which was first estimate of the acceleration, which was generated by having a 1 second time spacing, gives me one estimate of the true acceleration. As I let that 1 second become half a second, then quarter of a second, and on and on and on and on and on, I will see this ratio converge to a number, and that number is the true instantaneous acceleration. In fact, the one of the greatest contributions of calculus and Newton, therefore, is this idea of instantaneous motion. Now, why is this idea of instantaneous acceleration important? If you go back to a very first lecture and your old high school physics, the instantaneous acceleration times the mass is equal to the force causing it. So, at the moment we are not really bringing in force, but we do need to know what the instantaneous acceleration is to understand the forces that the system is experiencing. Or conversely, if I know the force that a system is experiencing, I can only calculate the instantaneous acceleration. I cannot calculate any other acceleration, and from that instantaneous acceleration I should be able to deduce the rate of change of velocity and the rate of change of position. We will see how to do that in just a moment. So, to recap, usually in an experiment I get to make x as a position of time. So, this is position known as a function of time, and from that we can calculate u as a function of time. So, velocity, and then even acceleration, which could be a function of time. And the way these are related, u is dx dt, a is du dt, and using the first equation we have written here, I can also write the acceleration as the rate of the second derivative of position. Now, I can generalize this to 2 dimensions or even 3 dimensions in general. So, if I define x vector, which we will call the position vector, and x is given by some x E x where form the unit vector set defining our Cartesian coordinate system. Okay, so, if I now start with this definition of the position vector, I can define a velocity vector as dx dt and the acceleration vector as dv dt, also dx dt squared. Now, in Cartesian coordinate systems, these are fairly elegant to explicitly write out. So, this would be dx dt Ex plus dy dt Ey plus dz dt Ez. For brevity, we will use the dot notation given by x dot, dot indicating time derivative. Likewise, acceleration is x double dot Ex double dot z double dot Ez. So, if time is my independent variable and I have the position x as a function of time, position y as a function of time, position z as a function of time. If I know the positions of these particles as explicit functions of time, I can do this one differentiation to get the velocity of that particle at various instants of time. Notice that these three functions x dot will be functions of time. Likewise, the x double dot, y double dot and z double dot will also be functions of time. So, this completes our discussion where we choose time as the independent coordinate. So, what if I want to make observations in a spatial coordinate with spatial coordinate as the independent coordinate? Okay, so let us take our one dimensional system. So, let us say the particle is constrained to move on a road that is given by that, and this is my fixed observer O. I have this particle P moving on this one dimensional road, and I am willing to make observations. So, in other words, let us say let us take the old example of a car. I make observations of the car's motion at various positions. So, let us say this is at x equal to 1 meter, let us say this is 10 meters from the origin. So, this is x equal to 0, let us say, and this is some x equal to 11 meters. So, if you think of these, let us say I have people positioned at these locations that are able to record the instantaneous velocity of this car, the instantaneous speed of this car as it passes those points. Can I deduce the acceleration from this information? Okay. So, if I know u as a function of x, so which is basically the velocity as a function of position, how do I get the acceleration? So, this goes back to our basic definition of what acceleration is. These are valid only if time is my independent coordinate. So, if I have space as my independent coordinate, I can rewrite A as du dx times dx dt. This is simple chain rule, and from this, and using u is nothing but the rate of change of position, u is a du, a the acceleration is equal to u times du dx. So, if I know u as a function of x, so let us say I have, like I said, people at various positions making these observations. Here is a way to calculate the instantaneous acceleration at an x position. So, when I say a equal to u du dx, u is a function of x, a is also going to be a function of x. Okay. So, if I know the velocity at various positions, here is a way to calculate acceleration, and I can use the same idea of du dx being, in this case, limit delta x tending to 0 u at x plus delta x minus u at an instant x divided by delta x. So, this idea of making observations at two stations x and x plus delta x, and as the distance spacing between these two stations becomes smaller and smaller, our estimate of du dx, not the acceleration, du dx converges to a number, and that number multiplied by the instantaneous velocity u at that x location gives us the acceleration. So, this is a second way of analyzing the motion of a system. So, if I have observations along a path at spatially discrete locations, here is a way to get the information pertaining to the acceleration. We will always end up with the instantaneous acceleration. It is still the instantaneous acceleration only because it is at some fixed x location. It is not instantaneous in the context of, or in the definition of it being a time instant, but it is instantaneous in the context of it being at a localized spatial location. So, you can talk of this not as instantaneous, but it would probably more appropriate to call it the local acceleration. So, at the particular location I have an estimate of the acceleration. So, if I now put these two together, so A is u du dx in one dimensional motion. If I am using position as the independent coordinate, and A is du dt if I am using time as the independent coordinate. So, if we ask the question, I need to get to the instantaneous or local acceleration as the case may be, which is the correct choice of independent coordinate for my system? The answer to that really lies in making observations as easily as possible. So, I choose one of these two, whether I choose time or whether I choose space, I choose one of these two based on ease of measurements. That is, at the end of the day, that is going to be the overriding reason to make a decision on this. Okay. So, let us take the second case using position as the independent coordinate and generalize it from one dimension. So, in 3 dimensions what would it look like? Remember, acceleration, even in the old way of defining things, acceleration is a vector. This is a 3-dimensional vector. So, the instantaneous velocity was a vector, instantaneous acceleration is also a vector. Likewise, if I generalize this, if I know the velocity as a function of spatial position, so this is called the velocity of the particle is known as a function of the position vector. So, let us understand what this actually means in 3 dimensions, in 3 Cartesian dimensions. This notation V vector as a function of x vector basically amounts to V itself being u v w. Okay, u itself is the x component of the velocity, y component of the velocity. So, a particle moving in 3 dimensions generally has 3 components of velocity, and the 3 components of velocity, each component is a function of the position vector, which itself is defined by 3 spatial independent coordinates. Okay. So, 3 coordinates x comma y comma z define the position of this particle, and u, the x component of the velocity, is could be in general a function of all 3 spatial locations, all 3 coordinates x, y comma z, v and w. So, for this instant, if we generalize acceleration, which I will write as ax ex plus ay ey plus az ez, where ax ay az are the local accelerations. So, this is different from instantaneous accelerations. These are local accelerations at the position x, y, z. In the 3 unit vector directions. So, Ax is the component along Ex, Ay is the component of the acceleration along Ey, Az is the component of the acceleration along Ez. Now, I have to relate this acceleration to the velocity field, and without going into the details, this comes out to be V dotted into the gradient of the velocity field. So, I will simply write out one component of this and talk about it. This would be u du dx. Now, since u itself is a function of more than one variable, in this case u would be u partial derivative of u with respect to x, partial derivative of u with respect to y, so this is the case, the acceleration, instantaneous acceleration, I am sorry, not instantaneous, but local acceleration in the x direction of this particle is actually given by the summation of these 3 terms, u times the partial derivative of u with respect to x plus v times the partial derivative of u with respect to y plus w times the partial derivative of u with respect to z. We are not going to go much further in this sense, because this is not relevant to dynamics, to rigid body dynamics, but those of you that are interested in fluid dynamics will have no choice but to go into this kind of a detail, primarily because that is the system that is the independent coordinate choice that is the easiest to analyze fluid mechanical systems. We are going to constrain ourselves to looking only at rigid body systems, which are easier analyzed by using time as our choice for the independent coordinate. I will make only one point here, in that look at the x component of the velocity or x component of the acceleration in, let us say, planar motion. So, if I have a body only moving in 2 planes in a plane in such a fashion, if at these 2 locations, if the velocity is instantaneous and is tangent to this path instantaneously and locally at that point, the rate of change of the x velocity, meaning u, in the y direction du dy causes an x component of velocity. Okay, so, dou u dou y, which is this term here, is responsible for x component of velocity. Okay, so, if I, and this is kind of the origin of what we talk about as centripetal force or centripetal acceleration. One could, so this is kind of one simple way to think of motion in one direction, or rate of change of the motion in the y direction causing an acceleration perpendicular to that coordinate direction. Okay. All right, we will stop here. We will look at some example problems in the next class.